Good evening. My name is Lorenzo Perella. I'm here from physics. I'm here from Clark Woolman's Physics 116 course to go over quiz 5, specifically number 4. Though first, it's important to set up this problem that on a rainy day with a temperature of 33 Celsius, that a traffic policeman who's using a 10.525 gigahertz frequency aimed at a radar horn at a car coming towards him at a certain velocity. Once we have to find out that this police officer finds that the beat frequency is 5.0858 kilohertz, and we're trying to find what the speed is in millimeters per second of the car towards the horn. Now, to get to this, we first need to set up the equations necessary from problems 1 through 3. First is the sound speed of air in meters per second. To do so, we take 331 meters per second, which is the standard, multiplied by the square root of the temperature given in Kelvin divided by 273.15 K. That would be 331 times the square root of 306 divided by 273. That gives us 350.42 meters per second. Then we need to set up the equation for the frequency in terms of V as it's coming towards the car, of the perceived person, which is the police officer, and also when it is moving away from the police officer, which in the first one is the given Hertz value, 10.525 times 10 to the power of 9 times 350.42 plus this velocity of the car divided by 350. And then for F of equals for number 3 is the perceived answer for number 2 times 350.42 divided by 350.42 minus the velocity of said car. It's a car. I'm getting confused with something else, but that's not the issue here. Finally, we get here, where we know that the beat frequency is equal to 5.085 kilohertz, which is equal to the F observed divided by the standard frequency, which is F obs divided by minus 10.525 gigahertz, and that's the absolute value. So to get the answer, we take the F obs, which is 10.525 times 10 to the power of 9 hertz, plus the beat frequency hertz, 5080 hertz, which gives us 10.52 hertz. And then 1/2 of the beat frequency allows us to find the median range. And from there, we know that the F observable is the original frequency times 350.42 V plus V over 350 is equal to the original frequency plus half the beat frequency, which is 1.052 E10 hertz. And then that amount we divide by the amount that we got for the F observed and multiply it by 350.42, which is 1.0000241 times 350.42, which equals 350.4246 meters per second. And then when you subtract that amount from the original meters per second that we got equated in number 1, we get a velocity of 8.45 E5 meters per second. Now, in order to convert this to millimeters per second, we take the answer and multiply it by 1,000. This ends up with a total value of 0.0845 millimeters per second. Thus, this car is going very slowly, which is relatively speaking because we are using very high valued numbers for our hertz. And when you're taking a very high high number divided by a small number and multiplying it by an even larger number, you will end up with a small number. Now, the question states that I need to discuss this final piece of how the beat frequency allows for the speed to be converted. And as we've illustrated, such a speed is possible, even if it seems unlikely. Thank you for your time. This has been Lorenzo Perella for Clark Wellman's 116 Physics class. Have a wonderful evening.